Good morning. Okay. So, to many developers, JavaScript engines like Hermes seem like black magic. Something not done by regular engineers, but brought to us by wizards whose spells we couldn't possibly hope to understand. But they're not black magic. They're just code, like everything else. And in this talk, I'll explain at a high level the elements that go into JavaScript engines like Hermes, so that you too can understand how they work. My name is Radek Pietruszewski. I'm the CTO of Nozbe. I'm also the author of open source React Native libraries like WatermelonDB and ZACS, both of which were introduced at React Native EU. And I'm thoroughly unqualified to give this talk. Tsvetan is the real expert here. I'm not a systems engineer. I don't do C++ for a living. I have no background in compilers. I don't even have a computer science degree. This is by design. I hope to show you this way that you don't need these qualifications to understand how compilers or interpreters work. So the inspiration to do this talk came to me after writing this blog post in March, in which I took a look at Hermes codebase for the first time ever with no prior background. And I set out to make the JSON parser twice as fast with this provocative title, which I did. So you can check it out for a lot of Hermes details under this QR code. OK, so how does Hermes work? Well, really, we should ask ourselves, how do compilers and interpreters work in general? There are some ways in which Hermes is special, but most of the basics cover all of languages. So let's look at table of contents, and this is a lot to talk about in 30 minutes, so I won't go into details, just like basic understanding of the parts, and you can talk to me later for more details. So we'll talk about lexing and parsing, which is where you go from source code into something more understandable to the engine. Then we'll talk about writing a simple interpreter. Then we'll talk about writing a fancy interpreter with bytecode. We'll briefly touch on what makes Hermes different. And we'll also do a speedrun of garbage collection. So let's begin in the beginning. We have this very simple JavaScript program. It's just a function, say hello, and it says hello in the console with some number, right? So how do we go about executing that? Well, the first step would be to lex it or tokenize it, which is to take this source code, which is just a string, and turn it into a flat list of tokens. And the first one for this program will be a reserved word function. So reserved words or keywords are things like function, for, if, break, return, and so on. And then after that, we'll see an identifier say hello. So identifiers are your names that are not reserved words. Notice that in source code, we have a space in between that, but this is just syntax. This doesn't matter at runtime. So during lexing, all white space is cut off. After that, we have some punctuation. Each piece of punctuation gets its own token. And we get identifier console. Notice, again, comments don't matter at runtime, so we cut that off during lexing. And then we get to the string literal. So there are many ways in JavaScript to express strings with single and double quotes. There are escape characters. And because they're just syntax and they have to be turned into the actual character in memory, this is what lexer does. This ambiguates these different ways of expressing strings as well as numbers. See, in the source code, we have a hexadecimal number, but in the end, it's just 255. So that's a speedrun of lexing. And hey, it's just these 4 files. You can read the source code. And then, from this flat list of tokens, we want to get structure. So during the parsing stage, we turn these tokens into a structured representation of the source code, which we call an abstract syntax tree, or AST for short. Abstract syntax tree sounds a bit scary, but let me show you. It's not that bad. So let's build the AST for this program. And all of that is a function declaration. This will be our first object or AST node that we'll build. And the function declaration has a name, which we call ID. And say hello, these names are also their own AST objects, which we call identifiers. It doesn't take any arguments, but it also has the body. And the body is just a list of statements contained within the function. In here, we just have a function call. And function calls in AST we call expressions. A call expression has the function being called, which is called callee. That's a lot of call. And if we called a function foo, the callee would just be an identifier foo. But console.log, we call that construction member expression with object console and property log. And then arguments, which is, again, string literal and numeric literal. So that's the AST. OK, I did skip like program and block statement, but those are minor details. And if you want to like really understand in detail how JavaScript AST works, or ASTs of other languages, I highly recommend astexplorer.net. This is a web-based interactive tool where you can just dump a bunch of source code and see the abstract syntax tree, and like highlight different parts and see how they correspond to the source code. By the way, this is also an excellent tool if you want to learn to make Babel plugins, ESLint rules, or code mods. This is how I've learned, and so I do recommend it. So let's say you're writing a parser. Here's a fun detail. What does this mean in JavaScript? Well, you have to parse it somehow. But actually, funny thing is, it depends. See, this could be a regular expression equals b divided by 1. I don't know why you would do that, but this is valid JavaScript. By the way, as we all know, regular expressions divided by a number are not a number. But this could also be preceded by a valid expression, in which case it could be something completely different. It could be something like a divide equals b, with just a comment that says 1. And the a could be a complex expression. So that's the sort of fun details that you have to take care about when writing a parser to disambiguate that. And there's also ambiguities in JavaScript around these characters. So comparisons versus bit shifts versus type parameters in Flow or TypeScript or JSX identifiers, all of which are parsed by Hermes. So you don't really need to know this, but I think it's interesting. When I told you that there's the lexing stage and the parsing stage, in reality there's just parsing, which is kind of a pipeline. And the parser keeps asking the lexer to advance, which is to say, it keeps asking it for the next token. But it tells the lexer where it is in the AST, the grammar context. Because the parser knows if in this place in the structured representation of source code, if it's possible to see a regular expression or division. So that's how it works. So that was a speed run of flexing and parsing. Let's talk about writing an interpreter. A simple interpreter, like way oversimplified from reality. So here we have a very simple JavaScript program, 1 + 2 × 3. How do we execute that? So let's first draw the AST that we got from the parser, and I'll do that in text form this time. So we have a binary expression, which is like 1 + 2 or 2 × 3. That's a binary expression with operator plus, and it has left and right operands. Left is just a numeric literal 1, and right is another binary expression, which is numeric literal 2 times numeric literal 3. I hope you're with me. So you could write a simple AST interpreter, and you can imagine that each of these AST nodes is just an object, and it has a method execute, which would evaluate the expression within that AST node, execute its side effects, and return the value it evaluates to. So this is pseudocode, of course, but imagine you're implementing the execute method for binary expression, right? You look at the operator for the AST node, So for addition, you'd execute left and right operand and add them together. It's not so bad. So let's quickly run through executing that. So execute binary expression. OK, we need to execute left. Numeric literal just evaluates to itself. And then execute right. So we drill deeper, one AST node deeper, execute that. Execute left and right. 2 times 3 is 6. 1 plus 6 is 7. OK, that wasn't that hard. Now let's do a complicated 2-line program. So const a equals 1. OK. And then console log a plus 2. Let's draw the AST. We have a program. This has a list of statements. We have a variable declaration. The name is identifier a. And the value is numeric literal 1. So that's const a equals 1. After that, we have an expression statement with a call expression, so just a function call. The callee is a member expression console.log. And there's one argument, which is binary expression identifier a plus 2. OK. So now let's execute that. We start from program, and we execute program by executing all of its body's statements from top to bottom. So let's execute variable declaration. How do we do that? Well, we need a place to store variables. And let's just call this place execution context for now. So we execute the value of variable declaration. In this case, it's just 1, but it could be a complex expression that we need to drill down to evaluate. And we put that under A in the execution context. OK. And now let's go to the call expression. So again, first we evaluate the properties of the call expression. So first the callee, member expression. For member expression, first we look at the object. Now, how do we execute an identifier console? We execute that by looking up console in the execution context. And console is predefined. And it's an object, right? And then from console, we look up log, because that's the property of the member expression. And we get a reference to a function. So we'll evaluate the arguments. This should be simple. So binary expression, drill deeper, evaluate identifier a by looking it up. So this is going to be 1. Numeric literal evaluates to itself. 1 plus 2 is 3. So now we have the function reference and the values that we pass as arguments. Now here, console log is a predefined function. So it's defined somewhere in native code. So we call that, and we get undefined. If it was a user-defined function, we'd get a reference to the AST node of the function declaration, and then execute one by one the statements inside of the function declaration body. So that's how the program is executed in a very simple AST interpreter, by traversing the abstract syntax tree from the roots deeper and deeper, executing each node individually. Well, it's more complicated than that. So some details that you'd have to take care of. So when executing something like a function declaration, you're not executing its body. You're just putting a reference to the function on what I called execution context so that it can be referenced later. It's only when calling functions, so when executing a call expression, that you'd actually look into the body of the function declaration and execute that. Second complication is hoisting. So in JavaScript, you can use functions and variables before they're declared. So in reality, when evaluating a function or a program, you have to do it in 2 stages. First, you need to look up all of the function and variable declarations to hoist them, and only then execute the rest. Then variable scoping, I said execution context, but in reality, it's going to be some sort of stacked contexts, because every function and every block introduces a new scope where a variable name can mean something else. And of course, you need some sort of call stack when calling functions to know where to return to. So now let's talk about interpreting the fancy way. Let's talk about bytecode. So bytecode is the sort of modern approach to writing interpreters, and this is how Hermes works. In this approach, instead of traversing the abstract syntax tree and executing that directly, we go through the AST to compile it into bytecode and then execute that in a different step. So bytecode is a flat list of very, very simple instructions. If you ever saw assembly code, it's kind of like that. So bytecode is like a pretend JavaScript assembly for a pretend JavaScript machine, which is just your program. And that's why you often hear the word, that's why you often hear the word virtual machine when talking about something like Hermes. It's a bit confusing. It's not about true virtualization. It's just about the idea that the bytecode is kind of like assembly code, and your interpreter is then kind of like a virtual machine executing that. So let me show you how that would look like. Again, same program, and let's see the first line of the bytecode. So in the first instruction, we will load number 1 into register 0. So just like in real CPUs have registers, our virtual machine also has registers. They don't map to real registers, it's just an array of values that we reference with a number. Okay, we load 2, we load 3, and then we have instruction multiply. That's going to take as arguments register 1 and register 2, and multiply that and put the result in register 3. So that's what I meant by very, very simple instructions. It's kind of confusing to look at that, like why would you want to do it this way? But these instructions are so simple that you can't even pass a number to multiply. You have to put it in a register first and then reference the register. And after that, after multiply, we will add together. Okay, I have a problem with my slides, sorry. There we go. We will add together register 0, which is our 1 number, and register 3, which is the result of multiplying 2 times 3. I know it's a lot of numbers, sorry about that. Put that in register 4, and that's it. This is not real Hermes bytecode. It's like a simplified version to make it a bit easier to look at. And then our very complicated program. So again, const a equals 1, we'll load 1 into a register, and then we'll set local. So let's introduce the concept of locals, which will hold the local variables. Again, in reality, it will be like different stacked contexts for different scopes. And notice that in JavaScript, you can never ask a variable, like a reference for its name. So there's no point of keeping it. So from now on, A will only be known as local 0. Okay, and then for console log. To get console log, we first need to get the global object. So global is implicit, but in bytecode, we'll explicitly get the global object and put it in register 1. Then we'll get by ID. That's the instruction that will take an object and ask it for its property and put that in a register. So we get global console and then console.log. And now in register 3, we have the function reference. Now let's prepare the arguments. So we get variable a, which is local 0, into a register. We get the number 2, add them together, and now we can call the function. Call the function in register 3, which is console.log, with the argument from register 6, which is a plus 2. And put the result in register 7, and console.log returns undefined. So that was bytecode. It's strange to look at, I know. Why would you do that? In short, performance. Bytecode is CPU friendly. So traversing AST means that you're jumping throughout memory to get the properties of all of these objects. But in the bytecode approach, you do that once when generating bytecode. And then you have this flat, this left to right buffer of instructions. And we can represent them textually, but real bytecodes are a dense binary format. So it's just good for modern CPUs to execute because more fits in cache and stuff like that. I didn't talk about how to generate bytecode. It's similar to the way you do interpretation by executing the AST. So you traverse the AST, but now instead of evaluating and returning the value, each node will have a generate function that will append to the list of instructions in bytecode. And the bytecode approach also allows for further optimizations in an easier to do way than on a tree-like structure. So you might have been confused, like what's the matter with like loading one into a register, then into a local, then back into a register. Well, the reason why is this is easy to generate because you go through each AST node and that's what that will generate. But you can take that and in a separate step, you can optimize it. And Hermes can do that, and that would look something like this. So this was a very brief explanation. If you want to learn more and get pretty deep, I highly recommend this series of YouTube videos by Andres Kling, in which he takes his JavaScript interpreter JSLib and turns it from an AST interpreter into a bytecode interpreter. It's many hours, okay? But it's pretty approachable. Okay, so in short, executing JavaScript. We have flexing, then parsing into AST, we generate bytecode, and we execute that bytecode. What makes Hermes different is that after lexing and parsing, we don't generate bytecode right away. Instead, we generate something called intermediate representation, which also looks kind of like bytecode, but a bit more high level. And then there are multiple optimization passes on the IR to find common sub-expressions, eliminate dead code, and so on. And then we generate bytecode from the IR, not from the AST, and execute that. And of course, in Hermes, all of these steps, except for execution, happen ahead of time. If you want to learn more about what makes Hermes different, I recommend as a refresher Cvetan's talk from React Native View 2019, where Hermes was introduced. With this context, I hope his talk will be more approachable. So let's do a speedrun of garbage collection. So as your JavaScript program is executing, you're going to create a lot of objects. And most of these objects are short-lived. You're going to use them once or twice, and then you don't use them anymore. But you're not telling the engine to get rid of them. We have to do that automatically. And there's a standard, simple technique for garbage collection, which is called mark and sweep. So let me explain that. Let's draw a graph of all objects in your program, right? You have the global object, so like window or something like that. And you put an object there as a property. There are more objects. Sometimes they point to each other. Maybe it's an array. An array holds its items. There are ways, less direct ways to make an object accessible. So for example, you could set timeout or add an event handler. And then the JavaScript engine will hold a reference to the function you're passing. And this function will hold references to everything in its scope. So the general idea is that objects have to be accessible somehow to remain alive. And they're accessible if you can get to them from garbage collection routes, which is mostly like global object, indirectly for like events, and local variables on the stack. Okay, so some of these references will disappear over time, and these objects will become inaccessible, but we don't know that immediately. So when memory usage is high, we stop the world, stop executing, and garbage collect. And in the mark phase, we start from the global object, or from garbage collection routes, to be precise, and we traverse the graph of objects, and every object that we can reach, we just mark as in use. After we're done with that, we run the sweep phase, in which we look at all objects. So instead of starting from an object and traversing it, we look at the heap of all objects in memory from left to right, and everything that's not accessible, that's not marked as in use, we just get rid of. So that was a speed run of garbage collection, but it's really as simple as that. What makes real-world garbage collectors difficult, and something people do PhDs on, is performance. We don't want to stop the world every now and then to collect all the garbage. We want all of this to run in parallel as much as is possible to minimize the pauses when garbage collection runs. And that's what makes garbage collection difficult, not the concept. If you want to dive deeper, I would start with Hermes documentation. Hermes has two different garbage collectors, a simple one and a slightly more complicated one, and it goes into some detail to explain how that works. And if you want to dive really deep, I highly recommend posts on WebKit blog by Philippe Pizuot, where, like this one, retreating wavefront concurrent garbage collector, which sounds very smart and is one of the state-of-the-art garbage collectors. You need an afternoon for this blog post, but it's very, very cool. So sadly, we're coming to the end of the presentation. I hope I gave you insight into basics, the elements that go into writing a compiler, an interpreter, a JavaScript engine. But 30 minutes is just not enough to go deeper into details. So talk to me throughout the rest of the conference. Ask me questions. I'll tell you a lot more. And you'll find me on the internet, on Twitter, on Fediverse, and on my blog. And yeah, we do very cool stuff with React and React Native at Nozbe. So if you want to be hired, that's the email. Thank you.